So in the last session, we touched on fine-tuning with GRPO. And in this session, we'll zoom into the one component that makes or breaks the whole thing, and that's the verifier. And it's the thing that decides what essentially correct means in the context of training. So we'll focus on reinforced learning with verifiable rewards, and let's jump into it. So kicking off, to fully understand kind of reinforced learning and the kind of rewards models that people have used, there's two core ones, and that's reinforced learning with verifiable rewards, so RLVR, and then there's reinforced learning with human feedback, and that is essentially where you have a learned reward model that's trained on human preferences, and it sits in the loop of the training. It's very subjective and quite expensive to build comparative to a verifiable reward. And because of that, you can start to add biases. It can be very kind of fuzzy and is subjective in its reward scoring kind of style. Whereas on the other hand, you have verifiable rewards, where the reward comes from a deterministic program, so something like a math checker, a unit test runner, and so it's in this scenario, it's either like a hit or a miss. It's very cheap, it's objective, and it's reproducible. So that's the trade-off between the two of them, that RLVR is very good for things that can be programmatically checked, like maths and code, but for things like poem writing or prose writing or so on, you kind of need that human subjectiveness to define what is good and what isn't, and so that's where RLHF comes in, and obviously because of that, it's a little bit more compute intensive and a lot harder to build. Okay, so moving on and kind of understanding that verifiable reward loop, because that's what we're focusing on in this subject, is RLVR. So for each prompt, we sample n completions, verify one against the checker, and then assign rewards. Keep the verified correct ones as training data, and then update the policy, and then repeat it all. In this scenario, kind of the policy refers to the model. That's what they call it. In the workbook that we went through, we keep the model deliberately small, and it sometimes produces wrong answers. And so because of that, we are able to see the policy actually improve, because training on a policy that passes everything is kind of pointless. Another thing to call out in the reward process is the reward asymmetry. So you can see for a match, there's +1 for correct, but only -0.1 for wrong. So a much smaller penalty for failure. So this is because early on in training, most things will fail, and with having a small negative reward for a miss, we make sure that things don't completely collapse, and the model doesn't steer towards refusing to answer or trying to come up with ways to get around answering questions, like maybe just taking a number directly from the question and then spitting that out. And so in this way, we try and, lean it, trying to train it to go for that big reward rather than trying to, if it was an even punishment early on in that training, probably wouldn't help it too much. So let's move on to another very important piece, important concept with RLVR. Is that, yes, we're trying to we've got our verifier that's checking against ground truth. But we have two different training algorithms that consume those verified rewards, and that's GRPO and DPO. So GRPO was talked about in the last session, and it means group relative policy optimization, and it's essentially a reinforced learning algorithm that nudges the model weights to make a high reward answer more likely. And essentially the hint is in the name, group relative. So for each prompt, it samples a group of answers, then scores each one relative to the group's average. And so if it's above average, it's reinforced, below it's discouraged. And so with that, it's kind of cheaper and simpler, and it's kind of the algorithm that's used behind DeepSeek R1. Whereas we also have DPO, so direct preference optimization. And in this, it trains directly on pairs, a preferred chosen answer versus a rejected one. And it tries to push the model towards chosen and away from rejected. Normally, those pairs come from human preference labels, but in RLVR, the verifier creates them for free. And a correct completion equals chosen, and incorrect one equals rejected. There's no real reward loop, and no sampling during training, just supervised star loss of pairs. And because of that, it's very stable and easy to run. So, and we can see that kind of here where we get our verified correct, verified incorrect, and we build up those pairs for DPO style trainer, and then we take that group relative, versus group average versus result, and then train from that. Okay, so the two consumers in the workbook. I guess one last thing to touch on is once you train against the verifier, there's always that Goddhart's rule of law, which states that when a measure becomes a target, it ceases to be a good measure. So in our workbook that I'll show you shortly, we essentially want to try and avoid our policy from funding blind spots. So, we want to avoid it from parroting numbers from the prompt, exploiting the extractor, and so on. And so in this workbook, we also shipped kind of a hack signature detection, where we flag things like if they only gave the right answer but no visible work, or they just pull numbers directly from the question, whereas yes, that might be the right answer, but have to show you're working. And we also have an append only audit trail. So this essentially records every verifier decision, and that file is the answer when someone asks, was this trained on honest rewards? So yeah, let's jump into the workbook. So in my workbook, I actually dropped the model down to GPT 3.5 Turbo because we wanted to get some wrong answers and see the model improve. And using GPT 4 Mini, which was already suggested, was just too good. On top of that, we try and make sure that the final answers that are given sit inside this boxed nomenclature. So we kind of, that helps us find the final answer, but also see the working out. Okay. Here we added a few questions with expected answers and ran those. I think one interesting thing was the original verifier that was in this workbook was slightly brittle, where it was giving the right answer, but the verifier wasn't actually extracting that answer. And so I had to make a few improvements there. We also got a few false negatives, where I say it wasn't extracting them correctly. And then we did end up getting one full failure. So that was good to see, which means, we can improve our model. And then we have Goddhart's law, where, you want to flag the hack signatures and log every verifier decision to an append-only audit trail. So both very important. Yeah. Okay. Here we are building those preference pairs for the DPO style trainer. And lastly, we built our own verifier. I chose one that checks for JSON, schema conformance. And because of that, the kind of reward I went for was fractional, not binary. Because you want the model to try and improve slowly. So does it pass? Is it an object? And as each one passes, you want to give it more points, and so on. Whereas if it was just binary, that's JSON that passes, that's JSON that's not. Well, then early on in the training, kind of, it won't essentially, climb and try to improve as it goes. So, yeah. And a very important thing, detecting that hack behavior, because they are tricky. So, all in all, it was a great session, and thanks for watching.